So here we have a rundown of the Colab notebook for all the numpy foundations for deep learning. Most importantly are the fundamental operations on matrices. So numpy has uh, matrix support. Uh, So you declare the matrices as NP arrays, and there are built-in operations for dot products and also uh, uh, element-wise multiplication. So I didn't know this, but after doing this collab, I learned that this operator is kind of like a shorthand built-in operator for matrix multiplication. That's kind of neat. Um, so here, yeah, basically we just walk through the fundamentals of matrix multiplication. For two matrix to be eligible to perform matrix multiplication, it is required that they have shared the same dimension on the inner side. So this two side, they can have any arbitrary dimensions. They don't have to match each other. But this two, if we have A times B multiplied by B, then this side of the dimension, the inner dimensions have to match. So yeah, that's basically for the matrix multiplication. And the connection with matrix multiplication to neural nets to deep learning is that in deep learning in neural nets, we have tensors, which are also just essentially neural nets, that are constantly performing matrix multiplication between different layers. So input, you have inputs time multiplied by weights, and you have the output, which is being fed to the next layer. So yeah, this is the shorthand operator for matrix multiplication. And another interesting behavior, I guess, kind of like an overload for the plus sign, the plus operator when it comes to tensor or matrices, is that it's what it called broadcasting. So if you have like a proper array, like a proper tensor or proper matrix, and you plus it with a scalar value. Let's just say it's just one, right? And this is like a 3 by 1 matrices. And broadcasting basically just stretch this one dimension one dimension matrix or essentially just a scalar value to match the shape of the matrices. So whatever the it stretches whatever the smaller shaped matrices to match the bigger ones. So yeah. So now we have the connection between having this bias is that in neural nets or in deep learning, we always have a bias uh, kind of aside from like weights times inputs. So then we can model like more complicated models or relationships. So yeah, this is the connection. Yeah, so this diagram or visualization just tells you how the broadcast works, right? If you have like 10, 20, and 30 as the bias vector, then in order to perform the operation, right? You want to this is the proper matrix, and when you perform the plus operator on like uh what's it called, the 1 by 3 matrices as a matrix, it basically expands or stretch the smaller bias matrices to match the proper shape, the dimensions of the left-hand side, so that you can perform a proper matrix addition. And you have this one. So if we go back here, we look at the operators, right? Yeah, like I said, the bias uh, matrix is a smaller one. It's a smaller dimension matrix. But when you perform the broadcasting, it automatically stretch to match the shape. So yeah, so we have those all those broadcasting. Um, yeah, like I said, the broadcastings. So here we touched the different kind of activation functions. You have sigmoid, you have ReLU, you have leaky ReLU. Uh, yeah, so these are pretty straightforward when you code. They're mathematic forms in Python or in NumPy. Yeah, and this is like the visualization for all these activation functions. Wait, this is a cell? Oh, also, yeah, here you have softmax, which wasn't present in the previous one. Uh, yep. So after the activation functions, so activation function is the layer that's sitting between the hidden layer and the output layer. So this is kind of important. Uh, yeah. So this section talks about various mathematical functions that are provided by NumPy. Specifically those concerning arrays or in our context, matrices. Um, so yes. So like you can see here, you have broadcasting, you have scalar operators. Yeah, these are scalar operations. And in this section, you're going to see how we put up all the above kind of basic building blocks and build in a altogether a neural net using all we have shown above. Right, so you have your starting matrices as the input and weight and bias. Um, so then we start with so here you also briefly touch about different data types, right? You're going to have a lot of floating numbers instead of just nice looking integers. So here we examine the shapes of the tensors, or rather dimensions of the matrices. Here we are using a famous example of the meanest handwritten digit image recognition data set. So yeah, so here we talk about how to slice the matrices. This is important so that we can do the matrix calculation, matrix multiplication uh, using like a divide and conquer kind of approach. We just do them batch by batch, like a subset of the start matrix. So yeah, we have them starting and stop indices. And yeah, so after all these preparing and slicing, we move on to um, doing so. Yes. So this visualization talks about basically talks about how you can slice up the original matrices and just like kind of solve like a subset of the problem, and you can have intermediate results, right? So for this row, and multiplying this column, you end up with the this section of the result in the final matrix. And also, this is just an intermediate result. This will get updated when you move to other rows and columns. So this is very powerful operation or technique for saving memory and, employing parallelism to accelerate operations. Because in real production or more complicated training models, we the matrix size is going to be very big. We could easily have hundreds of rows or columns or even thousands, if not more. We can't fit the entire matrix into memory or GPU memories and do the operations, do the multiplications in memory. So to do it, we have to slice them up. We have to do them sections by sections, row by rows, columns by columns. And this also makes it possible to do the matrix multiplication in parallel. So yeah. So like I said, so here we talk about batch processing, which is exactly what I was talking about above, right? Yeah. So that's the end of this collab. Thanks for watching.